advantages of the reference frame theory that I can calculate or find the torque. Good? Yeah. And simply, if we recall the total power into the system, Pn. Pn is equal to what?
P over 2
3
في VQS IQS زائد VDS IDS زائد 2 V0 I0 زائد VDR IDR VQR IDR و V0 2 V0 I0.
So simply, I'm having power input to the stator and power input to the rotor. Right? Yeah. I'm having a power input to the stator and power input to the rotor. So Pn is 3 over 2 VQ IQ S plus VDS IDS plus 2 V0 S I0S. This is for what?
stator
So I'm having also
rotor
So also I'm having 3 over 2 VQR, and forget the dash, IQR plus VDR IDR plus 2 V0R I0R. Yes? Good? Yeah. And if we recall the voltage in the voltage equation in the QD0 reference frame. VQ of S was equal to what?
RS
RS.
I
It was small, huh?
yes
So it's
RS
RS IQS plus
plus
d by dt of lambda QS plus omega lambda d.
lambda d
Lambda
ds
ds. And omega here unspecified. Until, huh? So this is the voltage equation in the arbitrary reference frame theory. Now, Vd of S will equal R of S IQS
DD
plus
IDS
IDS. I was copying the line. The human brain. ds plus d by dt of lambda ds here minus omega lambda qs. For the zero, I will not write it.
okay
In the end of the day, it will not contribute to the output. And this is for the stator.
stator
بس الروتر W minus W.
Yeah, there S go to R and W go to W minus.
W
So here VQR will equal to RR IQR plus d by dt of lambda QR plus omega minus omega R lambda dr. And finally, this is that, finally I'm having the VDR, which equal RR IDR plus d by dt of lambda
dr
dr minus omega r lambda eqr. So if I multiply this by the current IQ, I need those, huh? And here I multiply by IQS, here I will multiply by IDS,
IDS.
and here I will multiply by IQR, and here IDR. Good? And simply, I think last time, to make it simple for me, I decided to do omega equal to 0. Yeah. So if omega equals 0, for the stator there is no induced voltage due to rotation.
yes
So I will not carry it with me. I don't need to calculate that part of the power. Why? Because in the end of the day, the Pn
no rotation
will equal certain omicloses
Omicloses plus energy.
plus
Something
the rate of change in the rate energy, let's say, rate of change in field. And finally here what I'm having, the converted power, the power converted. Now what I'm looking for, the part that there is omega there, omega r. Huh? So if omega equal to omega 0, there's no omega here, and this is the only part I needed, correct? Yeah? So if I collect the terms, or you need me to write it in one? Okay, let's write. So Pn in total will equal to 3 over 2. Now here I will have Rs IQS squared, yes, plus IQS d by dt of lambda QS plus, here omega I don't have it, 0. No? So this term is not there. Now the second term is Rs IDS squared plus IDS d by dt of lambda ds. Now all of this term is either ohmic losses or rate of change in the field. So it will never contribute to the output.
Yes.
This is for the stator plus. Now here I'm having 3 over 2. So I will have RR IQR
Square
plus IQR d by dt of lambda QR.
minus.
Then I will have minus omega r lambda dr IQR. Then I will have plus RR IDR squared plus IDR d by dt of lambda dr plus omega r lambda QR IDR. Good. Now I will collect the terms that contribute to the output, which is a term
Omega.
contains omega. Good.
لو اوميجا مش زيرو يعمل contribution
No. By the way, the output is omega rm multiplied by the torque.
يعني بس اوميجا.
Yeah, this is omega is something virtual. I'm assuming my reference frame is rotating by what? By arbitrary speed. Now I'm assuming my reference frame is rotating by 0 speed. Yeah? I can also drive the same expression if I assume omega equal to omega r. In this case, the rotor will never contribute
The stator was.
to the converted power, the stator will. Yeah?
بس لو
In general, I can do it both, which means that I can assume that I'm having omega
Certain
and omega r. In the end of the day, I need to specify the reference frame that I'm working in order to calculate the torque expression. Good? But here you will see that either I can describe the torque in terms of the stator quantities or the rotary quantities. But in the end of the day, they have the same magnitude.
Stator current.
البي انبوت دائما شو ما كانت قيمة اوميجا تكون نفس القيمة.
Now the power input in general depend on what? The power output and the efficiency. Correct? Yeah. So if I change the reference frame, this will never change the input power. The system is not changing by changing the reference frame value. Yeah.
بس لا وانا بسأل عنه انه لو في terms فيهم اوميجا بالستيتر بصير مجموع الاربعه terms ولا برضه ما باخذهم؟
Okay. Now simply here, if you have omega, take it.
مش ضروري تكون اوميجا ار.
In the end of the day, the torque is equal the power converted over what? Omega r. Yes. Yeah. Now, I can give you the torque in terms of the arbitrary reference frame. Yes. Now, if you need to solve, you need to fix the reference frame. Yeah. Can you solve any problem arbitrarily?
No.
In the end of the day, you will tell me that fix your frame. Tell me your frame is rotating by which speed. So if I'm fixing the speed, there's no problem now. It will become a number. Yes. function of omega r, not omega. Yes?
Oh.
Good. But simply why I choose omega 0? In order to swing some terms. I don't need to take all the terms.
Oh.
Then I will do it when omega equal to omega r. Yeah?
We will have the same, except it
We'll
will be
have-
IQS instead of
The
IQR.
torque will be the same, but it will be described in terms of the stator variable. Here, it will be described in terms of the rotor variable. And in general, you know that we like to describe anything in terms of the stator variable. Why? Because we can measure it. Yeah? I cannot measure, for example, if I'm having a storage cage, can I measure the rotor current? No. So how you can measure? Yeah. So in general, we prefer to describe any term, let's say, in terms of the stator. Okay. So now let's collect the terms. So collecting the terms now, I will calculate what the power what developed. We agreed that. Yeah? This is ohmic. Ohmic losses would never contribute to the output power. This is also will contribute to rate of change, feed energy, store energy. It will never contribute in the output power. So the remaining term must be what? The converted power. The power converted. Huh? So the power converted now will equal to what? Who can give it to me? 3
over 2
over 2
omega R
omega r.
في
لامدا كيو ار
Okay, lambda q r
I D
اي دي ار
I d r minus
minus
lambda
lambda
d
d r
r
I
I
q
q.
r.
Correct?
Yes.
Good. Now from here, can I calculate the developed torque,
yes
Yes.
which will equal to what?
نفس الفينومينا.
The power developed over what?
omega
نفس
Omega r mechanical.
Yes.
هاي
This is what electrical omega r. Yeah? Omega r mechanical.
P over 2
Yeah, there's the P over 2. The relation between the electrical speed and the mechanical speed. So this will be omega r mechanical. So this will equal P over 2, 3 over 2, and in the end of the day, I'm having lambda q r I d r minus lambda dr iqr, which means that here I'm having the torque expression, correct? In terms of the rotor pattern.
torque مش omega R mechanical equal P over 2 electrical المفروض
Omega r I'm equal to what? 2 over b.
2
Omega r. صح?
اوكي
فكر P over 2
2 اوفر بي
According to Patrick. Huh? You should go down. So, huh? 1 over it. صح ولا
صح
Okay. Good. Now someone will say, what about if I'm assuming that the rotor is rotating by omega r speed? Yeah? What about if I'm assuming omega equal to omega r? In this case, the rotor has no omega r inside. It will be
Yes.
cancelled. Omega minus omega r. Correct? Only I will have what?
State.
The state. So who can give me now the power developed? It will be 3
P over 2
over 2
omega
Now remember, what I'm having, the first thing I will have, omega r, lambda
QS
lambda ds it was, I
I
cubes.
D
اي كيو
Yeah? Minus
minus
omega
Omega
r,
r,
lambda
lambda
qs, I
I
ds.
ds.
Correct? Those.
yes
Those terms. I multiply here by IQS, and here I multiply by IDS, and I'm collecting the terms, correct?
Okay.
So from here I can calculate the developed torque, which will equal 3 over 2 P over 2 and lambda ds IQS minus lambda QS IDS. Yeah. Good. Of course, I can exchange in between. So if I need to represent it in terms of the current, I have a relation between lambda Q and the current. Yeah? But if it's in terms of the stator, let's say flux and current, this is described in terms of the stator pattern. Yeah? Here, it was in terms of, let's say, the flux of the rotor and the current of the rotor. Yeah? And I can exchange in between. The two values are the same. The values are the same. If I'm describing the torque in terms of the stator quantities, it will be the same as describing the torque in terms of what? Of the rotor values. It's like what? I'm giving you 1 meter or 100 centimeter. The same. The same, huh? This is a roughly speak, huh? Here it will be Newton meter, huh? The same it will be. Not one will give you Newton meter and the second one will give you million Newton meter. No. Okay. Now, if I exchange the torque in terms of the current, not the flux linkage, I can write it as TE, I can write it as 3 over 2 P over 2 IQS IDR minus IDS IQR. So here it's described in terms of the current. Here it was described in terms of flux linkage and current. Flux linkage and the current. How I can go? Simply I have Q. For example, QS equal to what? You remember it? LS IQS plus M IQS plus IQR dash. Yeah? The same thing here. So I can represent IQS in terms of this one and lambda DS, lambda QS in terms of the current. So I can get this one. So now let's see. Which is easy to describe? The current in the QD reference frame or the current in the ABC? QD, well, count the terms, man. Just count the terms. Here I'm having what? 4 terms. The other is constant, correct? 4 terms. There, maybe I need 21 terms. Yeah? So in terms of terms, this one's more simple. Yeah? Someone will say, what about if I can make the reference frame rotate such that all the flux of the rotor is pointing toward the dx. Now you know that if you have vector, the flux, if you have vector, it will have 2 components. Yeah? Let's say lambda r has 2 components, correct? One is lambda dr and the second one is what? Lambda qr. Yes? Now imagine that this vector is, all of the vector is pointing toward what? Lambda dr. So lambda qr will equal to what? 0. Yeah? So if lambda qr equal to 0, this means that now I will have a simple expression, correct? Yeah? In the 2 terms. So from there I can highlight what we call the vector control, such that I will know which component will control the torque and which component will control the flux. For example, the beauty of the separately excited DC machine is what? Is decoupling in the control. Why? I know if I need to control the flux, I need to control what? The field current. the field circuit. Huh? If I need to control the torque, I will control what? The armature circuit, correct? This is very straightforward. Can we project this concept to the three-phase system? The answer is yes, using what? The vector control. Relying on the QD reference frame. Good. So now let's try to highlight the field-oriented vector control. Reference frame, Clark and Prague. There's two reference frames. The famous one is Clark transformation, and there's Park transformation. So one is using, let's say, from ABC to DQ. Second one say ABC alpha beta DQ. Yeah. Someone say that I will propose a transformation which is power invariant, the scaling factor. Someone say no, I will use amplitude invariant, the 3 over 2 phase. Huh? From 1960. By the way, someone will say that the science is saturated from the 19th century, by the way. Now what we are recalling, actually. We are recalling what's already done in the 19th century, but with the powerful tools we have. Not only the power electronics, the computation capability. For example, in their time, if they need to solve the differential equation, they will spend more than, let's say, certain time. Now we can solve it with no time. In their time, they use a lot of approximation. Now we can relax this approximation, correct? So most of the sense actually is due to the 19th century. Tesla, Ivanov, let's say, Maxwell, Ibn Sina. Yeah, actually. No. الجبر. جبر الخطي. Actually, they claim that Pythagoras is not the inventor of fair theory. It was in the paper. Yeah, but you know that. In that time, there's no communication. So if someone in Europe did something, and someone in Asia did the same thing, it will be two contributions. There's no, let's say, communication like now. Yeah, now you can just Google it, huh? Google it and you can find everything. Okay. So let's start with the field-oriented control. So let's. So. Or what we call it the vector control of the induction machine. Now, to highlight the concept. Imagine that this is my reference frame theory. I will start from the ABC reference frame. This is the AS. This is the BS. And this is the CS. And I'm having a rotor. And the rotor is rotating by omega r. Let's assume this is the rotor axis. And with R plus generality, I will assume that the terminals of the rotor is shorted. So either I'm using a squirrel cage induction machine or wound rotor where the rotor's terminals are shorted. So this means that VAR, VBR, VCR is equal to what? Zero. Yeah? So this is the coil for the rotor, this is the coil for the rotor and the B, and this is the C, let's assume, and those are what? Are short. Yep. And this one is rotating by which speed? Omega. Now, in general, there will be a flux. Correct? In general, there will be a flux. Let's assume that this is the direction of the flux. Let's assume that this is the lambda R. Now, I'm having the freedom to assign the reference frame. In theory, I can put it anywhere. Now, the trick is how to capture. Yeah? The trick, how to capture the point that you need to put your reference frame in. Correct? So let's assume that I'm lucky. Yeah? It's my lucky day, and I can put the D in the direction of the lambda R. Understood what I'm doing? So this is the, let's choose B. So let's assume this is the DRE. So 90 degree is what? Is the QRE. And E here refer to what? That my reference frame is rotating by which speed? The synchronous speed. Omega E.
تو لما ار بتدور بايش؟
Synchronous speed.
Synchronous.
The flux is rotating by synchronous speed.
Synchronous speed.
Any electrical signal is rotating by what? By synchronous speed. Correct? Yeah? So the reference frame is rotating by
Synchronous.
omega E, which is the synchronous speed. Good? Yeah? So simply, the D here is the magnetic axis. Yeah? Oh. Now, any vector lambda R as a vector, can be described as lambda dr plus lambda qr, correct? Yes? Yes? Now, due to my selection, all the flux is pointing where? So lambda qr equal to what? So this is the information I can get. Huh? So from here, from this selection, I can say that lambda dr is equal lambda r. Yes? And lambda qr is equal to what? Zero. So this is the good selection. Huh? Someone said it's good selection. Yep. Good. And for simplicity, let's assume that lambda r is constant. The flux is constant. I need to keep the flux at certain value. Let's assume it's what? The rated value. The best conditions for what? For the machine. Yeah? So let's assume that lambda r is what? Is constant. Until here, did you understand the assumptions? Yeah? So someone will say how we can put it there. Later on we'll describe how we can put it there. So now, let's assume you are lucky. This is your lucky day, and you managed to put the dr where pointing toward lambda r. So this assumption, this condition, will say that, or will give you the simplification lambda dr is equal to lambda r, and lambda qr is equal to 0, and I'm assuming that the flux in the rotor is what? Is kept constant. Good? So let's start with the equation of the vector control. Let's see. Now, let's start with the rotor voltage equation. Now, you know that VQR was equal to what?
Zero.
Yeah, 0 equal to
R
IQR plus
D by
d by dt of lambda qr plus
Omega.
omega what? Omega E.
Omega Omega
Omega
E.
E. Why? My reference frame now
Yes.
is rotating by which speed? The synchronous.
Synchron.
Omega E minus
Omega.
omega R lambda dr.
Dr.
Yeah? VDR equal to what? 0, which equal to RR IDR plus D by dt of lambda dr minus omega R E minus
Omega R.
omega R
Lambda QR.
QR. Good. Now, by assumption of my reference frame,
This term is zero.
this term is equal to what? By assumption of lambda is constant, d by dt of constant value is equal to what?
Zero.
So IDR equal to what? IDR equal to what?
Zero.
Yes. 0 over R. So, from here, this term will equal to 0. Why this term equal to 0? Because lambda QR is 0. This term will equal to 0. Why will equal to 0? By assumption that lambda R is constant. So in the end of the day, because I'm assuming that the VA, the VB, the VC and the R is 0, so VD, VQ and the R will equal to 0. Short circuit or squirrel cage induction machine. One rotor shorted or a squirrel cage. So from here I can get that IDRE will equal to 0. Why here I'm adding E, later on I will not add it. To say that this quantity is described in the synchronous reference frame. No? Good. Now what about the QR? Now let's see what information. This for sure is 0 because the value of QR equals 0. So IQR will equal to what? I can solve it with respect to what? To IQR, right?
Yes.
So IQR will equal to what? Minus
Omega R.
omega E minus omega R is omega slip.
Yes.
Yep. You know that. Minus omega slip lambda dr over
R.
R. Yes? Good. Oh. Now, let's try to represent IQR or lambda dr. I need to, let's say, describe. So simply here, I can say that omega slip will equal to what? Minus, rearrange R IQR over
Lambda.
lambda dr. Now, if I know omega slip, by the way, and I know omega R, I know the synchronous speed that I need. So I need to find omega slip in the end of the day. Similar to the view graph. Remember, if I need to compensate for the slip, I need to calculate omega slip and add it to omega R.
Yes.
So now omega slip here has equation, let's say, relation with the rotor circuit. In general, I cannot measure the rotor quantity. Can I measure the IQR? If I need to measure IQR, I need to measure IR, IBR, ICR, and do the transformation, correct? And in general, I can't measure it. Someone will say, wait. You know that in the end of the day, yeah, they will have certain value. It's shorted, man, huh? Shorted. Huh? Simply, I need it. I need the transit value, actually. So, now let's see. I need to represent IQR in terms of the stator value. Okay. Now, the flux linkage. Do you remember lambda QR equal to what? In terms of the current? LR I QR plus M. It was الأمس we call it. I think الأمس. إلام. That's right. إلام. I Q R, correct? Plus I Q S, correct? Yeah. Now simply, no?
الام مش ام
The same. any dam
LM over 2.
that LMS
Shear over 2. أو لا.
3 over 2.
3 over 2.
When I give it to you, I give it in terms of M or LM?
M.
M? Okay, let's do the M. It will be the same. So this can be written as LR IQR plus M IQS. Yes or no? IQS. Yes. I'm collecting. LR now is equal to what? The leakage inductance plus the magnetizing inductance. Now, correct?
Yes.
Good. So IQR will equal to what now? Can I solve this one with respect to IQR? Yeah?
لامدا كيو ار ناقص كيو اس.
Yeah, but remember, this will equal to what? By assumption. It's zero. Huh? You see it? So now, can I solve this one? Yes, I can solve this one. So I can say IQR will equal to what? Minus M
IQS
over L R IQS. Yep. So I can put this one where? Here. Yes? Good? Good. Now, lambda R, lambda dr will equal to what? Lambda dre will equal to what? It will be equal LR IDR plus M IDS, correct? Now this one equal to what? 0. So simply this means that this will equal to M IDS. Now this one also I will put it here. Yes? So if I do so, what I will have? If I do so, omega slip now will equal to what?
RR
Okay, RR
over LR
على الار
over LR
IQS over IDS
IQS
over IDS.
over IDS. Yes? Now, tau R equal to what? No, negative is already 18 by this one according to the backlog here. Yeah? Tau R equal to what? LR
LR
over.
over RR.
So this will equal to what?
1
1 over
over tau
tau R
IQS.
IQS over IDS. Yes. Good. So now we have expression of omega slip in terms of what?
Stator.
Of the stator
Stator
quantity.
quantity.
The stator current. Can I have it? Yes.
Yes.
I have, in general, for undrive system, I will measure the current actually. I will measure the IA, IB, IC, then I will do the transformation. Good. Good. Now, the torque. The torque expression was what? Now let's see. Now TE now can be written as 3
Over 2.
over 2 P
P over 2.
over 2 now IQS lambda dr, we have this one IQS lambda dr. I think we have the previous was what? Lambda ds lambda, okay, lambda ds IQ, okay, this one, okay. So I'm having another expression here, which is actually will be M over LR IQS lambda dr minus I ds lambda qr. It will be the same expression. Now I need to describe the torque in terms of what? Of the stator current and the rotor flux linkage. Why this is important for me? Because I'm having information for the rotor flux linkage. Lambda dr is equal to what? Lambda r. Lambda qr equal to what?
0.
So now, in the synchronous rotating reference frame, the E, and according to my selection of pointing the reference frame, we know that This one is equal to what?
0.
0. Why? Because lambda
Lambda
QR
QR
is equal.
equals 0.
So here what I'm having, this will end up to be what? 3 over 2 P over 2, let's say M over LR multiply by what?
IQS
I Q S E
lambda D R
lambda
R
lambda R.
E
Lambda R. Lambda D R E. So if I need to
O R
put-
O R
Oh,
lambda
lambda
D
R.
R
Or
equal
if I need to
lambda
put E, I will lambda D R E. Good?
Ah.
Now, lambda D R equal to what?
MIBS.
So this will equal to what, Ya Sulaiman, now? In terms of the current. Give it to me in terms of the current.
3 over 2
Yeah.
P over 2
Yeah.
IQS IDS interview.
So simply, this means that it's 3 over 2 P over 2 M square over LR IQSE IDSE. Yes? And let's put here lambda DRE equal to what? M IDSE. Correct? Yes? And let's put it in a box. Why I'm putting it in the box? See the beauty of the reference frame theory. Now the torque is proportional with what?
the stator current.
IQ, SE, IDSE. Why? All of that are constant. Yeah? And the flux is proportional with what?
The ID
IQ.
IDS.
Yes? Yeah? So similarly, this means that this will be the flux component of the current. Yes. Why? Because if I control IDS, I will control the flux. Yes? So similarly, this will be what?
The torque.
The torque component of the current. Yes? Yes?
Yes.
Oh, good. So this is the flux component of the current, of the stator current, of course, huh?
Mhm.
Of the IS. And this one will be what? The torque component of the stator current. Yes? Now, do you recall the torque in DC machine, in the separately excited DC machine? The torque was proportional with what?
Armature
The flux and,
and
the
armature.
So now the same expression, yes? Which means that the three-phase induction machine, the complicated system, become as easy as
Separately excited.
separately excited machine. I can control the torque and I can control what? The flux.
But under these conditions. Yes.
Under this condition, of course, yeah?
Yes.
I need to put my reference frame to be elegant where?
To the
lambda
Lambda.
lambda R.
asynchronous.
So now the answer, how I can do that?
لا هو وجه اشاره
وانا جاي نشرح ما شاء الله. لا تردد.
يميل ايوه
Good. So now the question, how I can do that?
ما انت مش بنقدر نفرضه زي ما بدنا؟
احنا فرضناه
ليه ما افرضه من الاساس مش عارف هذا دايركتلي.
Now, do you know where the problem is? The rotor of the machine, you don't know at which position it stops. So it can stop AR here, or AR here, or AR here, or here, correct? So the problem in the initial angle. Yes? The problem where? In the initial angle. So simply someone will say, I will put my reference frame, then I will do some kind of controlling such that my reference
The
frame will be
initial
shifted toward what? Lambda R and catch it. Then it will rotate with it.
With it.
Yes? Yeah? Because in the end of the day, there's initial value. There's initial angle. Yeah? Good. Okay. So how we can do that? So let's discuss with you the block diagram of vector control and how we can realize that.
استخدم كنترول.
Yeah, of course. Now, if I need to do the transformation, if I need to realize the vector control, I need to do the transformation. So, in general, I will measure IA, IB, IC. I need to do the transformation in order to get IDS and IQS, correct? So, the first thing I need to realize the transformation. So, if I'm assuming this one, the A, the B, and the C, I need to calculate the Q and the D. So here I need theta R, correct? Yes? I need here what? I need here theta. Which reference frame am I using? So theta E. Yeah? Because I will do the transformation in the reference frame theory, the synchronous reference frame. So this I, this will be the IQE, and this will be the ID. Now theta E equal to what?
Omega T زائد
Someone will say it's integration of omega E.
minus
Plus theta of 0, let's assume that I don't care about the initial condition, I will not care. Now, this one is equal to what? This one. This will be the integration of omega R plus
slip.
omega S. So the method of calculating omega in this way is called indirect. Yep. Indirect. So this is if I'm calculating the transformation according to this method, which means that I'm calculating theta using the integration of omega R plus omega slip, this will call the indirect vector control. So someone will say there's a direct. If this one is indirect, there must be what? A direct. Yeah, there's a direct vector control in which this theta is estimated from the flux linkage. Yeah, which is estimated. This is later on, if we have a time, we can discuss it. So now let's discuss the block diagram of the indirect vector. So we'll say that we have speed control. So this will be omega R reference. I will compare it with the actual omega. Omega R. Then this will go through what? A PI, speed control. Now, the output of the speed control is what? Is torque. Yeah? Now, let's see. Do you remember the torque relation was equal to what in under vector control?
P over 2 MC.
It was
3 over 2
3 over 2
P
P
over
over 2
P over 2
M square
M
or
square
over L R
L R
IQS
I Q S I
IDS.
D S. Yes? Good?
دكتور سؤال بس باللمدة دي ار هي بتساوي ام اي دي اس صح؟ احنا بنفرض انه اللمدة دي ار كونستنت
Yeah.
فالاي دي اس كونستنت؟
Enter here.
اه
Now, in general, I'm assuming that lambda R is constant. So if lambda R is constant, and because for linear magnetic circuit, it will equal certain inductance multiplied by the current. So if I need the flux linkage to be constant, the current must be what? Constant. So someone will say how I can choose the reference current from the rated value. Yeah. Good. From the rate. Good. So, if I'm having the torque, if I divide it over those terms, what I will get?
IQ.
Yes, correct. I will get I Q of S. So someone will say, reference, huh? Those are the reference. Someone will say, you know those because those are constant. Yeah? IDS is constant. You will give it. Yeah? You will give it. If you need to calculate the value, it will be from where? From the, let's say the rate. So this is the IDS as a reference. So this is multiplied by certain gain and this gain, this one, huh? Then it will be divided here. Yeah? And let's put n. N is specified for what? Numerator or denominator? Numerator. So this is the numerator. Denominator. The numerator. So this is what? So this means that T over this one. So I get here what? IQS. Yep. Now, and also here I'm having what? The IDS. Now, if I'm having IQS and IDS, I need to do current control. So for the current control, I can use either hysteresis current control, the most easiest one. So let's go with what? With the hysteresis. For the hysteresis current control, I need alternating signal, the best one. So I will do what? The transformation now from Q, D to where? The A, B, C. So here what I will get? IA as a reference. IB as a reference. And IC as a reference, but simply here what I need? Theta. Now, how to calculate theta E? Do you remember the slip was what? Omega slip was what? 1 over tau R. IQS over IDS. So I'm having the D and I'm having the Q. Huh? So simply, let's take this one from here. And this one here will enter to a function that's 1 over tau R IQ over ID. And this will be what? Omega?
Slip.
Slip. Now omega slip, if I add to it,
Omega.
I need space, huh? So let's make it down. Let's make space, let's make room for this one. So let's make room here. So this would be 1 over tau R IQS over IPS. And this will be what? Omega?
Omega slip.
Slip. So if I add omega slip to omega R, what I'm getting?
Omega E.
Omega E. If I integrate omega E,
Theta.
so this will be what? Omega E. So if I integrate it, I will get what?
Theta.
So let's assume this is that. Good? Good. Alright. Now let's do the hysteresis current control. For the hysteresis current control, I will compare the current with what? With the actual current. Correct? So simply, here if this is the inverter. So let's assume this is the where I will measure the phase. So this is the phase A, let's assume that here I will measure the phase B, and here I will measure the phase C. Those terminals go to the induction machine. Here I'm having access to the tacho generator, and this will be omega R. Don't forget to multiply it by P over 2. Yeah? In order to convert omega R mechanical to what? To omega R electrical. Otherwise, here you need to multiply by P over 2. If this one is what is the mechanical reference speed. Yeah? Okay. Now, this is the phase A. I measure the phase A. I will compare it with the actual current. Here, I will measure the phase B. I will compare it with the actual current. And here, I will measure the phase C, and I will compare it with the actual current. Yeah? So now, I will go to where? To hysteresis current control. You know that the first one, according to the system control, will give me the switches for what? Thank you.
لكن السويتش هاي تبع فيز A وباخذ له الانفرس تاعه لللو.
Yeah, so this is the A, this is the B, this is the C, and this is the S high A, S low A, S high B, S low B, S high C, S low C. So this one will give me the gate pulses for the upper switch of phase A, and the inverted for that will be what? The lower switch of phase A. The same thing for what? For B and the C. So those will go to the inverter. Good. Now, do you have any questions here? So if omega slit is equal 1 over tau r, IQS over IDS, this means that the reference frame is catching what? The rotor flux. Thank you. Yes.
ماشي شو بده
Do you have a question? Do you have any question?
بس عشان التليفون.
مش مشكلة. طيب. Okay, so let's start the quiz.